Welcome back to the Drug 300 video series for WVU. This will look at different types of data that we may have to work on. And it draws up 5 different contrasts, 5 different ways of distinguishing the data that we are working with. The first distinction is qualitative versus quantitative. And a very simple way of breaking this down and looking at it is the qualitative, looking at the qualities, just taking the word right there, the qualities of a particular attribute. So that attribute would then be represented, typically, it doesn't have to be, but it would typically be some kind of verbal description. Whereas quantitative data, being quantities, is working typically with numerical data. That I'm sure if you look hard enough, you can certainly find a qualitative data that looks like numbers. Things like the state highway routes. There's Route 7, there's Route 705. Those would be, yes, they're numbers, but that doesn't mean Route 705 is just over 100 times Route 7, whatever that would mean. So you can't always assume that just because it's a number, it must therefore be quantitative. Likewise, there can be a counterexample of it could be as simple as words written out, or more likely, words that we can then translate into some kind of numerical system. A common example that you have seen for that is the SEI system, where you may rate the instructor's effectiveness as excellent, good, fair, poor, or unsatisfactory, or some variation on those words. Those words then get, because they have an order to them, get turned into 5, 4, 3, 2, 1. And we then work with those numbers, even though those numbers, they may be useful for a quantitative analysis, but they started out as words. So this is not a hard and fast distinction, but to recognize qualitative data, on one hand looking at the qualities, it can be more free form as well, versus quantitative data working with numbers or things that are typically turned into numbers and would end up lending itself to the structure of statistical analysis. So we're working with quantitative data throughout the majority of this course. The second distinction between our data, and now we're looking at different ways of distinguishing types of quantitative data. Discrete data versus continuous data. The difference here discrete data has a restricted set of values. That set of values can typically means, it's not required, but it typically means they're going to be integers. So we might say 1, 2, 3, 4, 5. for the way we work with SEI scores. If you're looking at, say, the number of children in a family or the number of people in a household, if it's number of children, it could be starting at 0, going up to, there may not be a theoretical maximum, but in practice, we might say top out around, even at the most extreme example, around 18 or 20 kids. Again, you can't have 2.4 children in a household. And continuous values can take any number or any single possible value within a range. So it's typically, so it will be a real number. So the average income of a community or the income of a household, you can't have negative, but it's still continuous. And strictly speaking, it wouldn't be infinite. Even Jeff Bezos has an upper limit to the income. But you can make any single fraction of a dollar. So a person's income can be $38,423.53, or 54 cents, or 55 cents. There is a nearly infinite number of possible values that can be found within the data set. That's what makes it continuous. So many possible values, if not an infinite number of possible values. This becomes important because whether our data is discrete or whether it is continuous can affect some of the choices we make in how we describe the data for descriptive statistics, as well as how we carry out the inferential statistics and what choice of statistical test we use to analyze that data. The next distinction that we'll be making is individual data versus aggregated data. And this really gets to some of the kinds of questions you can ask and the conclusions that you can make about your data set. Individual data you cannot go any smaller, so to speak. You cannot get to a smaller scale. So I'll put that there. So no smaller scale is possible. To return to that polling example that I had in an earlier video, if we have individual voters, or in a COVID situation, individual patients, we cannot get any smaller. We cannot go any more fine-grained than the level of an individual person. So that would be individual data. In many cases, whether it's either not possible to collect individual data, whether it's illegal or unethical to use individual data for privacy reasons, or whether our questions, our hypotheses really work better with groups. That's when we would use aggregated data. So within the polling example, we might say, what is the overall proportion within Monongalia County that we think will vote a particular way? Or in the state of West Virginia, or the neighborhood of South Park. It doesn't, in a way, we can have many different scales for our aggregation. But it is grouped and within geography, it's often, it's not always, it can be grouped by income level, it can be grouped by other demographic categories, but oftentimes it is grouped by place when we talk about aggregated data. So the level of the county, the scale of the state, and so on. This is a very common pitfall, where if you are working with aggregated data and you do your statistical inferential test on aggregated data, your conclusions must be at the same scale of your aggregation. That means if you are looking at the relationship between income in counties across the US and the voting preferences across counties in the US, you might find that as the average income of a county goes up, so does support for a particular party. You can only really make that conclusion for counties. You can say counties with the higher income have a higher overall level of support for that party, but that doesn't mean every single individual with a higher income is going to support that party. So you cannot drill down to people or individuals within the group, within the aggregated data, when reaching your conclusion. You can only stay at the scale of your data. For that distinction of can you go smaller or can you not go smaller is individual versus aggregated data. We have two more types of distinctions here. The next one is, do we have primary data or secondary data? If we are working with primary data, we collected that data ourselves. If it's a poll, then that means you went and you got people to fill out that survey. You made the phone calls. You were actively involved in the initial generation of that data. If it's in a physical geography setting, you went out and you used the GPS to mark the locations of those bird nests. or where the trees of the appropriate species are found, or you measured the depth of the stream at regular intervals. It's always something where you were directly, personally involved in the collecting of the data. Secondary data, on the other hand, is where somebody else did that. Where it's data collected by somebody else, and then you are reusing it for this study. So where people may have collected data on the location of birds' nests for a particular project, to say, okay, they want to see what kinds of tree species the bird nests are found in. But you go along and you say, well, I'd like to use this data, but for something else, and I might use that alongside some other data I have. To say, well, maybe it's not the tree species. Maybe I want to look at the locations of those bird nests with respect to distance from streams. And so you bring in stream data, and you reuse that bird nest data that somebody else collected. Likewise, if somebody collected, like the Census Bureau collects demographic data and then makes it available online. When you go and you download that data off of the census website, you are not personally involved in collecting that census data, so it is a secondary analysis. In many cases, when we go back and think about the data collection stage, if it's primary data, you know you are getting exactly the data you need to solve your problem, to answer your overarching question. With secondary data, it may be good, it may be close, but it may not be the absolute best data available, but it's still preferable than going out and doing a full data collection yourself. And lastly, we get to how space is represented. Most of the time within geography, we are working with data that has space involved some way, shape, or form. And the question then is that explicitly spatial data or implicitly spatial data? If it is explicitly, the location of the data is directly, specifically within that data set. So you may have latitude, longitude coordinates or UTM coordinates to say this bird nest is at this specific location. On the other hand, we can often work with implicitly spatial data. So the data set that you download off the Census Bureau might say it's Monongalia County. That tells you where that data is associated with, even though there is no geometry directly in that data set. In many, many cases, we can take this implicitly spatial data and then using ArcGIS or other software, join it to a data set that is explicitly spatial, that says here is the boundary of Monongalia County, represented as a polygon. And then we can take that implicitly spatial data and join it to explicitly spatial data and use it within our GIS, use it within our spatial analysis. So those are these 5 different distinctions of the data that we can be using: qualitative versus quantitative data, individual versus aggregated data, primary versus secondary data, implicitly spatial versus explicitly spatial data, and discrete data versus continuous data. As always, if there are questions, please feel free to reach out. Have a great day. I will see you at the next video.